what happened was that I was asked to give a colloquium next week in kaist, an institute in Korea, and I decided to prepare. And I think I already prepared too much. As you can see around here, can you see the mouse, my mouse pointer? So there are already 70 pages, but the talk is supposed to be only 60 minutes, including the Q&A session. So it's clearly too many pages I already have, and I clearly need to cut many of the materials. And I just want to know how much I can speak in a reasonable speed, in a reasonable amount of time. So I just wanted to test it. And I decided that it might be not completely useless to try this strange form of outreach by putting up the link on the Twitter so that if, anybody interested can attend. So that's the idea. So the title is Quantum Field Theory, Mathematics, and their Recent Interactions. And but after I prepared the talk, it turned out that the following title is much better: Life Between Mathematics and Theoretical Physics. So the talk will be a relaxed type of talk, and you can ask me any questions during the talk. You can ask me, well, as I'm going to give this talk in English, I want to practice it in English, but because most of the audience are Japanese anyway, if you have questions, you can ask me in Japanese if you don't feel comfortable speaking in English. So let me start. So I'm usually categorized as a string theorist, and you can ask whether the string theory is physics or mathematics or mathematical physics. So I'd like to start by exploring what these words mean. So for that purpose, I think it's useful to have a two-dimensional diagram. So the horizontal side specifies whether the subject is related to the real world or not. And the vertical axis specifies whether the method used to analyze them is rigorous or not, right? And physics tend to be related to the real world, but at the same time, it tends to be not rigorous. On the other hand, mathematics is, well, almost by its nature, is a rigorous subject, but then oftentimes it is not related to the real world, and it just explores whatever interests the mathematicians. So what are mathematical physics? So the mathematical physics lies in between these two extremes, and but it can be itself much varied. And so this right-hand side is what usual physicists think of as physics. So anything related to the real world, whether it's rigorous or non-rigorous, is considered as physics by physicists. And then for mathematicians, independent of whether a subject is related to the real world or not, anything which is mathematically rigorous would be mathematics, as obviously. So where am I? So I think I live somewhere around here, which is not rigorous and not related to the real world. So you can ask whether there is any use in something which is not rigorous and not related to the real world at the same time. I want to say yes, and at least it's useful to the extent that I got invited to give this colloquium. But joking aside, I'd like to explore the relation between theoretical physics and mathematics by comparing it with the relation between theoretical physics and experimental physics. So in the case of the relation between experimental and theoretical physics, experimenters work very hard, and then they show new experimental results to the theoreticians. The theoretical physicists, in turn, think about the reason and compute many things. And eventually, they predict new phenomena or new quantities to be measured. And then experimenters continue their hard work. So this is the, well, rather schematic view of the relationship between theoretical physics and experimental physics. Here, I propose to exchange the role of experimental physics by rigorous mathematics. So the point is that mathematicians work very hard to prove something, and then they present new theorems to theoretical physicists. Theoretical physicists think of the physical significance of these theorems then, and then they predict or conjecture new theorems to mathematicians, which mathematicians can later work hard to prove. So as you saw, the relation between mathematicians and theoretical physicists are rather similar, in my opinion, to the relation between theoretical physicists and rigorous experimental physicists. So let me put the relation this way. So experimenters can touch the real reality by the experiment, right? And what theoretical physicists do is to sit idly, speculate, and suggest where to look. In contrast, rigorous mathematicians can touch Platonic reality by their hard work using rigorous mathematical proofs, right? And then again, theoretical physicists just sit idly, speculate, and suggest where to look. So as you see, both experimenters and rigorous mathematicians are similar in the sense that they can actually touch the reality, whether it is a real reality or the Platonic reality. So that's my the sense in which I say experimenters are very much like mathematicians to me as a theoretical physicist. So this is a tall order, right? And how does it work? Does it actually work? And I'd like to say that in some cases, yes. So let me start with an example. Once upon a time, meaning that it was in the 1980s, mathematicians were counting the number of spheres in a particular six-dimensional space called the quintic-Calabi-Yau. So you don't have to understand any of the technical terms here. Well, at some point in space and time, in this universe, there were mathematicians who were interested in these esoteric questions. And in 1979, Joe Harris computed the number of, well, size 1 sphere in this space, and there were 2,875 of them. 7 years later, Sheldon Katz counted the number of size 2 spheres, and there were 609,250 of them. So it was a laborious process. Honestly speaking, I don't know why these algebraic geometers were interested in this question, but, well, they were interested in their own work and they were computing it. Around the same time, superstring theory was born. It says the world is 9 plus 1 dimensional, which is crazy. But so to match it with the fact that our world looks 3 plus 1 dimensional, we need to call up the unwanted 6 dimensions into a very, very small space. It turned out that the same Calabi-Yau space is a nice choice for this purpose. So some of the physicists, string theorists, started studying them for their own reasons. So let me just show you a very typical animations of certain two-dimensional slices of the six-dimensional quintic-Calabi-Yau you often see in books and TVs, right? Eventually, I will post the slides itself, and you can click this link, which leads you to a Mathematica online page where you can find how to draw this picture, which contains also a citation to the original paper. So you will learn how to draw these animations. So, but in reality, it's a six-dimensional space, and this is just a two-dimensional slice of it. which is further projected into 3 dimensions, which is further projected to the screen, computer screen, which is just 2 dimensions. So what happened was that string theorists Candelas, De La Osa, Green, and Parks found in early 90 a vastly quicker but non-rigorous method to compute the number of spheres in the same quintic Calabi-Yau studied mathematicians. So please recall that in 79, the size 1 spheres were counted, and there were 2,875 of them. And then Katz computed in 1986 the size 2 sphere with this number of them. So what would be the size 3 sphere, right? So that's a very natural question. And physicists came up with this number. I don't want to read it out loud, but you can see it, right? So that motivated mathematicians to do their own way. And these 2 persons, Scandinavian mathematicians, computed that slightly afterwards. And they got a different answer, which is much more than what physicists got. So that was a big issue. And there was a joint mathematical physics workshop in May 1991 to resolve the issue so that each side can learn the other side. So this issue was not resolved at the spot, but both sides tried to debug their own computations. And finally, 1 year later, in July 1991, the Scandinavian mathematicians found a bug in their computation and reproduced the prediction by physicists, right? So now physicists and mathematicians both got exactly the same number of size 3 spheres within the quintic Calabi-Yau. So this was when the mathematical field called the mirror symmetry was born. So as you saw, the interaction between physicists and mathematicians are rather like the interaction between experimenters and theoretical physicists, in that one side predicts something, the other side try to reproduce it in their own way, and they gradually converge to each other's conclusion, and they agree with each other. So I took this detail from a very nice historical review by Peter Gallison, and that can be reached from this URL. And I very much thank David Morrison for giving me this information. So there are many other examples of such interactions between mathematics and theoretical physics. And I think I was very, very lucky to have been involved in one of them called the Matthew moonshine. So Matthew moonshine appeared already 10 years ago in 2010, April, right? So it was on 6th April 2010. So it's exactly today, right? 11 years ago. So that's interesting. And this was written by me and my former advisor, Eguchi sensei, and also with Oguri-san. And this was posted on high energy physics section of the archive. But then this was taken up by mathematicians too. For example, 2 years later, Terry Gannon wrote a paper proving some part of our conjecture rigorously mathematically. And then in last year, June, there's still ongoing work by mathematicians, this time called topological Matthew moonshine. So this Matthew moonshine is being investigated by mathematicians too. So that's another example. So what I intend to do is to give you an idea of what is this Matthew moonshine is about. But it's a long way to go, because I need to tell you what is quantum field theory, what is string theory, what are the Matthew groups, and then what is the moonshine. So let me try anyway. So what is quantum field theory to start with? It describes quantum properties of fields where fields are anything which extend along space and time, such as electromagnetic fields, which is just another name for the light, right? And also crystal vibration can be thought of as a field. An electron, which is point-like, can also be thought of as excitation of an electron field. So most of the things around us are fields, and if you want to examine them using quantum mechanics, then you necessarily have to deal with quantum field theory. The prototypical example is the quantum electrodynamics, QED. It describes quantized electromagnetic fields interacting with charged particles, electrically charged particles. It was established around 1950s, and a lot of development since then. So in this case, the interactions are between theoretical physicists and experimental physicists, and they match extremely well in QED. The prime example is the physics quantity called anomalous magnetic moment of the electron. So they agree to an astounding degree. So I can say that quantum field theory is well researched. QFT, quantum field theory, predicts quantities with high precision, and QFT agrees very well with experiment. But it is mathematically rather incomplete in the following sense. Quantum mechanics and general relativity are two topics you will hear first when you enter university as a difficult subject in physics, right? But it is already mathematically formalized in the following sense. They can be described to mathematicians in a sentence. So quantum mechanics is the study of unitary operators on Hilbert spaces, and general relativity is the study of the Einstein equation on manifolds. So again, you don't have to understand what these technical sentences mean mathematically, but the point is that from the point of view of the mathematics, they are at least formalized and they can be treated well within the method of rigorous mathematics. But quantum field theory is different. Nobody knows how to characterize or how to formalize what a quantum field theory is. I've been doing QFT for a long time, so I think I know what it is by heart, but I cannot describe it in a sentence. So there's a certain unformalizedness in this whole field, which is not particularly bad if you are a physicist, I should say. It's okay if you can't describe it mathematically. I mean, it's a problem of mathematicians, right? I mean, ancient Egyptians could build pyramids. And of course, that might be a bad thing because Pharaoh exploited their populations. But well, after 2,000 years or 3,000 years, they are tourist attractions, right? But well, all of this was done without formalizing geometry by Euclid. It was long before that when ancient Egyptians could build pyramids, right? So it is perfectly okay for physicists to be able to predict anomalous magnetic moment of electron to such high degree of accuracy, which is matched by experimental results. Well, it doesn't have to be formalized mathematically, but there's a flip side of the coin. So because QFT is not quite formalized in rigorous mathematics, it seems to have a tremendous power in bringing about new results in mathematics. Let us move on to string theory then. It is a quantum theory of strings moving relativistically. It turns out that, as I already said, it is consistent only in 9+1 dimensions, and it automatically contains quantum gravity. If you are a sane person, you will surely immediately stop doing string theory after hearing that it requires 9+1 dimensions, right? Because our world is 3+1 dimensions, as you can see by looking at this corner of the building, right? There are 3 lines meeting at a point. This clearly shows that the space is 3-dimensional, and there's an additional time direction. So the trick is that string theorists say that the additional unwanted sixth dimension is called up in a very small space. That motivated the physicists to study Calabi-Yau space, as I already said, right? And also, as for this quantum gravity aspects, well, reconciling gravity and quantum mechanics has been one of the long-standing issues in physics, and there are many competing approaches. String theory was not originally designed to solve this question. Rather, it was originally made to understand hadron physics, but it turned out it turned to be more useful for the study of quantum gravity. There are many who are passionately for string theory, and there are also many who are passionately against string theory. And you might ask me, does it describe the real world? I don't know. For me, what matters is whether it is platonically consistent. Again, I do not have any definite proof that it's platonically consistent because, well, it's not yet the rigorous mathematics. But it seems it is, and many mathematical predictions have come out of it. So suppose you want to study strings moving in Calabi-Yau. Well, it's very hard to draw what is going on. So this was the figure of Calabi-Yau I took from previous slides, and I draw a string, closed string in this case, on some point on the Calabi-Yau, and I wanted to show it moving within the Calabi-Yau. So please excuse my bad drawing. The point is that in the space-time point of view, the string becomes a two-dimensional sheet if you combine both space-like direction and the time-like direction. So it is done in terms of 1 + 1 dimensional quantum field theory on the world sheet. And instead of Calabi-Yau space, Matthew Moonshine concerned strings moving in some space called K3. What is a K3? It is a closed 4-dimensional space satisfying this equation. So this R is the Riemann tensor, and this is a standard 4-dimensional epsilon tensor, and you want to impose this condition. So, and you also need to demand that it is not completely flat. So you can think of K3 as a very nice space which is half flat in a precise technical sense. You don't have to remember that, but K3 is a nice space. In particular, it solves the vacuum Einstein equation with 0 cosmological constant. So if you like general relativity, it's a particular solution in all Euclidean signature, and it is closed and 4-dimensional. So K3 is named as such by mathematicians André Veilleux, honoring 3 mathematicians involved in the study of K3. The 3 persons are Kähler, Kummer, and Kodaira. So the names started all with K. So that's K3. And he also named the K3 after the beautiful mountain of K2. So you might have heard the news earlier this year that the Nepalese team finally climbed K3 during the winter. Sorry, K2 during the winter. Yeah. So the origin of Matthew Moonshine goes back to the work by Eguchi and Oguri in 1989. So Eguchi is my advisor, who unfortunately passed away 2 years ago, and Oguri-san is my long-term collaborator. He's a director of IPMU. So at the time, Oguri was preparing his PhD thesis under Eguchi, studying strings moving in K3. A central result in his PhD thesis is this particular equation, right? F of tau is 90q, 462q squared, 1,540q cubed, ... So this is basically the partition function of a string moving in K3. What does it mean? What are the mathematical significance of these integers? So in the rest of the talk, I need to explain this to you. So to understand it, we now need to turn to the role of symmetry in quantum mechanics in general, not just in quantum field theory. So everybody in the physics department will learn or we would have already learned that the angular momentum operator in quantum mechanics takes the following value. So if J is the total angular momentum, then the Z component of the angular momentum Jz can take the following value, minus J plus 1, dot, 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 J minus 1, comma, J. So there are two J plus 1 choices. So if the total angular momentum is 0, the Z component can only take the value 0. If the total angular momentum is 1/2, the Z component can only take either minus 1/2 or plus 1/2. If J is 1, Jz can only take minus 1, 0, or plus 1. So that's what you learn. So this is the quantization of the angular momentum. And for integer J, there are also traditional names. So the J equals 0 state is called S, and it has degeneracy 1. When J is 1, it's called P, and the degeneracy 3, and so on and so on. Everybody in physics department will learn or would have learned the spectrum of a hydrogen atom to the zeroth approximation by studying the Hamiltonian under the inverse law potential. And it looks like this. So the vertical axis is in terms of Reuleberg, and 1s state is here, 2s state, 2p orbital, 3s, 3p, 3d, and 4s, 4p, 4d, 4f, and so on. And p states, p orbitals are 3 times degenerate, d orbitals are 5 times degenerate, and so on and so on. So that's what you already know, or what you will eventually learn. And this degeneracy is related to the symmetry. The angular momentum operators L, X, Y, Z are, from mathematical point of view, infinitesimal generators of the 3-dimensional rotation group SO3, which is the symmetry of the hydrogen atom. And the total angular momentum J specifies how the symmetry acts on the quantum states. Equivalently, or mathematically, this total angular momentum J specifies the representation of the symmetry group SO3, and the degeneracy in physics language, physics jargon, is known as the dimension of the representation. And the spectrum of a hydrogen atom to this zeroth approximation shows accidental degeneracy in addition to the rotational symmetry. So the energy spectrum is determined only by this principal quantum number. So 2s and 2p are exactly degenerate at the zeroth approximation. So not just 1 and 3 fold degeneracies predicted by SO3, it actually shows 4-fold degeneracy, 9-fold degeneracy, and 16-fold degeneracies, and so on and so on. This is known to reflect a hidden 4-dimensional rotational symmetry acting on the hydrogen atom, and that's long known, but originally by Pauli and then Fogg, etc., and etc. So what you need to remember for the rest of the talk is that this degeneracy is related to symmetry. If there is an unexplained degeneracy, you can look for additional symmetry, which should explain this additional symmetry. The rotation group is a continuous group. There are also finite groups, such as the symmetry A5 of the icosahedron, which contains 60 elements. For the symmetry A5 to act on quantum mechanical systems, it needs to be represented by matrices. This is because quantum states are vectors in vector space. So in this particular case, an element G, or within this icosahedral group, is represented by 3x3 matrix. The size of the matrix is known as the dimension. In this case, it is 3. So a representation which cannot be decomposed further is known as irreducible representations. This is the analog of a state with a fixed total angular momentum. And the dimensions for A5 are known. So it's given by 1, 3, 3, 4, 5. And physicists have some traditional names for the representations, A, T1, T2, G, and H. And we physicists are perfectly happy studying various concrete systems with various concrete symmetries. This is the schematic structure of C60, also known as the Fullery. I don't know how it should be pronounced in English. It's usually called Furaren in Japanese, but surely it's not the correct pronunciation. And I took this figure from Wikipedia. So you have carbon atom, 60 carbon atoms, and connected in this way. The property of A5 is very useful when studying electronic properties of such systems. And I just Googled some papers studying the electronic spectrum of the C60. And surely you have this diagram showing the state, quantum state of fullerene. And surely they are marked by the representation of A5, and you have a lot of degeneracies specified by the representations. So what would mathematicians do when they are faced with symmetry? Well, some of them think rather differently from what physicists would do. So they say, let's classify all possible symmetries. Let's classify all finite groups. They have different mentalities. Any finite group is made of finite simple groups, just as any integer is a product of prime numbers. So our first step would be to classify all finite simple groups. And it has been classified. So finite simple groups are one of the following: either a cyclic group of prime order, ZP, or alternating groups, something called alternating groups, A5, A6. So A5 is the icosahedral group. And then also there are finite groups of Lie type, which are obtained by considering a continuous group over finite fields. And then finally, there are 26 sporadic groups, 26 individual ones. So the sporadics are named after the discoverers. So Matthew groups, which is the Matthew of Matthew Moonshine, was found by Matthew in the 1860s, right? There are 5 of them. And the others are named after the discoverers, except the last 2. One is Baby Monster, and the last one is the Monster. The proof of this theorem, this classification of finite simple groups, is said to be longest in the history of mathematics. It was announced to be complete in the late 70s to early 80s, with papers and preprints said to total 5,000 pages, more than 5,000 pages. Since then, some of the mathematicians are trying to come up with a streamlined rewrite of the entire proof in a single series of volumes. This project has been going on for decades. It already has about 3,500 pages, but it's not yet complete. So it's a very huge human endeavor. And because of this audience, and not today, but for the audience in kaist, I think it's interesting to remark the following point. So before going to the 26 sporadic groups, people were studying finite groups of Lie type, which is obtained by considering continuous groups over finite fields. The last 2 series of finite groups of Lie type were found by Rim-Hak Lee, a Korean mathematician, and they are called Lie groups. And for Japanese and Koreans alike, distinguishing Lie groups and Rie groups are very difficult because we don't have distinctions between R and L. Now, coming back to the sporadics, well, or other finite groups, when it comes to the data of finite groups, nothing can beat the atlas. So it's a very huge atlas containing lots of data of finite groups. You can estimate the size by comparing the book with the size of my hand. And this is an example page. So this is about M24, the massive group. Not as comprehensive, but equally useful is this Japanese math encyclopedia. So, well, if you need the information, because mathematicians have worked it out, you can look it up. So that's what I wanted to say in the last few slides. So I can now finally come to massive groups. There are 5 of them, M11, M12, M22, M23, and M24. They were found by Matthew in 1861 and 1873. The largest of them, M24, has this number of elements. So it's a big group, but not too big. And it is the symmetry of something called the extended binary Golay code, which was introduced in 1949, only 1 year after Shannon introduced his information theory, which was 1984. So this is the entirety of Golay's paper. So it's less than 1 page, but it's very dense. He tried to find find codes which satisfy a nice properties. He found 2. This is the binary Golay code, and this is the ternary Golay code. This was published in a journal which is no longer existent, so it's very difficult to get a copy of it, but you can find it. I found it in the Wikipedia page. So you might ask, what is a code? So this is a subject which you would learn in information theory in computer science course. I can only give you a very brief outline. So computers, as you know, use strings of bits such as 01, 011, 0111, right? But you cannot directly communicate them over long distance because transmission errors might flip bits. So if every bit is absolutely important, then once it was flipped, it is flipped, the information is completely lost and never can be recovered. So you need to find a way to add redundancies so that small number of errors per bit can be corrected reliably. And one such encoding is the Golay code, which encodes original 12 bits into 24 bits. So it has a almost 100% redundancy. And so it's a very secure, but reliable, but wasteful type of code. But it's a particularly symmetric code. So the symmetry is M24, the largest massive group, as originally noticed by Leach, mathematician Leach, famous for the Leach lattice in 1967. I have been emphasizing that all this talk is totally devoid of real-world contributions, but this Golay code was actually used in the real world. One famous example is NASA's Voyager mission. So some of the scientific data from Jupiter was sent back using this Golay code. So let me just play the video of the Voyager mission approaching the Jupiter. So this was the first artificial satellite, interplanetary aircraft, which reached Jupiter. It arrived at Jupiter around 1997, March. And I took this from NASA website. Here I need to add a disclaimer. So if you read the technical documents published at NASA those days very carefully, you find that this particular photographic image was not actually encoded by the Golay code because of this 100% redundancy. So apparently the scientists decided that it's perfectly okay for some of the bits consisting of this image of Jupiter be flipped, right? It wouldn't ruin the beauty of the majesty of the image of the Jupiter. Rather, where the place where they used Golet code was more sensitive, more data, the kind of data which is more sensitive to the flip of the bits, like the temperature and such numerical data they wanted to transmit from Jupiter. Also, Golet code was only used during the Jupiter mission. Apparently, they decided that they have a more economical way of doing it, and they switched to Reed-Solomon code, something called Reed-Solomon code, when Voyager approached Jupiter, sorry, Saturn and the outer planets. I have zero idea how the scientists switched the code in the Voyager mission in such a far place from Earth. But anyway, so I cannot say too strongly that Golet code had a real world use, but in some very distant way, I can say that M24 is related to the real world. So this is one excuse from me. And before talking about the Matthew moonshine, I need to talk about the original monster moonshine, because Matthew moonshine was the second moonshine. So for this purpose, I need to mention modular J function, which is a nice complex analytic function known from the 19th century. It has a Q expansion of this form, 1 over Q plus 196884 times Q plus ... And Mackay had the following observation in 1978. So these things all happened around the early 80s. The new finite simple group, the monster, as I already mentioned, which is the largest of the sporadics, was being constructed around that time. It was not perfectly settled that such a group actually exists, but well, they have good reasons to believe that it existed. And it has a huge order. But mathematicians noticed that the smallest non-trivial representation of that has dimension 196883. So Mackay noticed that this coefficient in modular J function is just off by one from the smallest representation, a dimension of the smallest representation of the monster. So he said there should be some relation, but that connects two distant branches of mathematics. J function has been known from 19th century in the context of classical complex analysis. On the other hand, the monster group is a finite group. So these two sub-areas of mathematics were considered very, very far apart at the time. And such a relation sounded too crazy back then. That was why it was called monstrous moonshine. Here, the word moonshine does not mean the moonlight. If you look up English dictionary, the word moonshine means foolish thought or illegally distilled alcohol. So that's the connotation these two words have. This monstrous moonshine conjecture was mostly solved around the early 1990s by FLM and also by Bolchers, and there have been many developments since then. The proof used ideas from two-dimensional quantum field theory. So that's all I can say about this original monstrous moonshine due to the time constraint. And I can finally come back to the Matthew moonshine. So let me remind you, in his PhD thesis, Oguri computed the partition function of a string moving in K3. So I quoted the central equation again, 90Q, 462Q squared, 1540Q cubed, ... So this is the generating function of the degeneracies of the energy states of a single string moving in K3. The coefficients mean that the first excited state has degeneracy 90, the second excited state has degeneracy 462, the third excited state has degeneracy 1540, etc., etc. So it's very analogous to the degeneracies of the hydrogen atom system I showed you many times, and you have seen or you will see in physics courses. Around the same time, there was also the following math paper called Finite Groups of Automorphisms of K3 Surfaces and the Matthew Group by Shigeru Mukai. So this math paper says that the possible symmetries of K3 space are not quite Matthew group, but very much related to the Matthew group. If you read the paper carefully, it says that the symmetry group is a certain small subgroup of Matthew group, M24. The precise condition is that there should be at least 5 orbits within M24 action on 24 points. So Eguchi-san, his advisor, thought that the coefficients Oguri-san found should be related to the Matthew group, right? So that was his observation. And nothing happened for 20 years. In the meantime, I became a student of Eguchi as well and obtained my PhD in 2006. In the summer 2009, August, all three were attending a physics workshop at Aspen. So there's a nice physics institute there. This is the building of the institute. There's a wild field around it. This is a ski resort in winter, but during summer it is used for various purposes. And although you cannot see, there's a small town around here, just below the ski slopes. So this is the Aspen Institute. All three of us were there. We decided to revisit the question on that particular day. I don't remember why anymore. We gathered and sit in a single room. I said, why don't we look up the table of representations in the Iwanami Math Encyclopedia, right? So this is the equation of PhD thesis of Uri-san. This is the table from Iwanami Math Encyclopedia. So 90 is twice 45. So there's a 45 dimensional representation of Matthew 24. There's a representation of size 231, and 462 is twice of that. 1540 is twice, 2 times 770. Similarly, 4554 is twice 23 times 99. And it goes on like this. There is a correspondence. So we thought about this relation for about half a year, but eventually we didn't find any other things to say. So we wrote a paper simply saying that there is a correspondence, but nothing more. And we submitted it to the archive, submitted to a journal, and it got accepted. So this is the beginning of the first page of the accepted version of the paper. And the journal title is called Experimental Mathematics. So there's such a journal, especially suited for this type of research. So if you would happen to do any kind of research activity in the future, please look for this journal and submit your results there. And as you could see, well, my contribution was literally only the suggestion that we should look up the table, right? So it was essential, of course, but it was also totally trivial. Anybody else could have the same suggestion, could have made the same suggestion. And in fact, Eguchi-san and Oguri-san could have looked up the same table in 1989 because the math encyclopedia or the atlas of finite groups have been in existence since then. I have zero idea why they didn't look it up, but somehow this became one of the most cited papers of mine. So this is basically the end of my talk. As I said, that paper was originally posted to the physics section of the archive, but mathematicians got also interested. Some of the mathematicians got interested, and some part of the conjecture was proved. And there have been more activities since then, even last year. So that was what I wanted to say. And I will stop my talk by showing you this summary. So in my opinion, experimenters and mathematicians are very much alike. So they can touch the reality. Experimenters can touch real reality, while rigorous mathematicians can touch Platonic reality, while theoretical physicists just sit idly, speculate, and suggest where to look. Thank you very much.